Hey, we're going to be covering Chapter 3, Linear Systems and Matrices, specifically Sections 1 and 2, Solve Linear Systems. We're going to be going over the two ways to solve linear systems, that is, graphing and algebraically. So first of all, let's just define a system of linear equations or a linear system, and that is a system of two equations having the form of ax plus by equals c and dx plus ey equals f. So this can really take the form of anything, so we could have 2x plus 3y equals 5, and then 4x plus 5y equals 1. Any constant that is not 0 can take a, b, c, d, e, or f. Now, a solution of a system of linear equations is an ordered pair that satisfies each equation, and it corresponds to points where the graphs of the equations in a system intersect, not interact. Intersect. So we could have two equations and the graph. So in a very simple example, we could have a line here and another line here, and this point here would be the solution of that equation, that system of equations. So that point xy satisfies a system of equations and corresponds to the point where those graphs intersect. So now that we've defined what a system is, let's move on to solving linear systems by graphing, section 3.1. So our ultimate goal is to find the solution of this system, and we're going to do that first in this section by graphing. So we've graphed this system here, the system that is 4x plus y equals 8, and 2x minus 3y equals 18. This graph is not to scale, but I've done it as best I could with this software, and we see here on the graph that the solution looks like it is 3, negative 4. And now we can check this algebraically by plugging it back into our system, as you can see here. We can see that yes, this is a solution of our equation, and therefore 3, negative 4 is our answer. And we solve this by graphing first, and then checking algebraically. So we're on page 154, and the book kind of takes a detour to classify systems. And we start off with a system that either has one solution or no solution. So the book says that a system that has at least one solution is consistent. If a system has no solution, the system is inconsistent. A consistent system has exactly one solution, and that is independent, and if it has infinitely many solutions, then it is dependent. So to break that down, we have this chart here. So one solution again is called consistent, whereas no solution is inconsistent. So if we look at an example, we can say that exactly one solution means there's one point that can satisfy the equation. So once again, we went over that, and if you plug it in, it makes the equation true. Graphically, we can think about that as so we have two lines, and they intersect at one point. So there's exactly one solution. Whereas if there's no solution, that means the lines are not intersecting. So two lines and they're not intersecting. This would be inconsistent, whereas this would be consistent. Now, a consistent graph that has one solution, this would be the same graph as this one, but by saying it is consistent and independent, we're defining it more specifically. Now, a consistent graph that has infinite solutions, so you would have your two equations, right, and they would each have a line that you're graphing. Now, if they end up being the same line, then it has infinitely many solutions because anything on this line, any point, is on both lines. So therefore, there are infinitely many solutions that work in this system of equations. So if we want to look more specifically at some better graphs that we have down here, we have the exactly one solution. So this would be consistent and independent, this one. It has an intersection at one point, so therefore has exactly one solution. Next, we have our line that has infinite intersections. So in reality, this is two lines here. Two lines, and it has therefore infinitely many solutions. And so that one would be consistent and dependent. Now, if there are no intersections, there are no solutions, and therefore it is inconsistent. So for a problem of this section, the directions would be to solve this system, then classify as consistent and dependent, or inconsistent. And again, let's just go over what those are. So consistent and dependent, that would be one intersection or one solution. Consistent and dependent, that would have infinitely many solutions. And inconsistent would have no intersections, therefore no solutions. So we have our system of equations here. 4x minus 3y equals 8, and 8x minus 6y equals 16. So if we graph these, we have this graph here. So we can see that this is actually the same line when we graph them, and therefore there are infinite intersections. And therefore we know that it has infinitely many solutions, and then it is consistent and dependent. So this is our answer here, consistent and dependent. So the second way we can solve linear systems other than by graphing is algebraically. So there are two methods we're going to be using algebraically, and that is substitution and elimination. Let's use substitution first. We have our equation 2x plus 5y equals negative 5, and x plus 3y equals 3. So this system of equations we can solve by solving for x first and then plugging it into the other equation. So we can solve for x or y first. We're going to solve for x in this equation. So we have 3, we have x equals negative 3y plus 3. And then we can plug this into the other equation, or substitute it, hence the name substitution. And we get we can plug in negative 3y plus 3 for our x, plus 5y. And now you can see that we have only y in our equation, and we're just going to solve for y. If we solve for y, we can plug y into the x equation, or substitute it. So we have x plus 3 times 11 equals 3. And x equals, that's supposed to be 11x here. X equals negative 30. So our final answer is negative 30, 11. Next, we're going to solve by elimination. So we have 3x minus 7y equals 10, and 6x minus 8y equals 8 for our system. So we're going to eliminate one of these variables. So we will set this up. We're going to write them one on top of the other like they are shown here. 6x minus 8y equals 8. We want to eliminate one variable by setting this up as an addition problem. So we're going to do that by, if you remember the property of plus 1 minus 1, you get 0. So that's how we're going to eliminate. We need to make 3 into negative 6, so it will cancel out with the 6x here. So we're going to multiply this entire equation by negative 2. So we get, this is from our first equation on top here, I'm just moving it down below. We get negative 6x plus 14y minus 20, and then just copy down the second equation underneath it. And you can see here that these x's will cancel out, and we'll just be left with y. So we have 6y equals 12. So we have y equals 2. Now to get what x is, we just plug this into one of our equations, and let's use the 3x one. So 3x minus 7, plug in 2, or substitute it. And then for x, we get 4/3. Our final answer is negative 4/3, negative 2. So finally, we have linear systems with many or no solutions. So we're going to solve this first one on the left using substitution. So we're going to solve for x. X equals 2y plus 4, and then plug it in. Our answer, we get to the point where we have 12 equals 8. And since 12 is never equal to 8, this is never true, and therefore there is no solution. For our next problem, we're going to solve this by eliminating. So for this problem, we need to multiply both sides by, well, actually we're going to be multiplying them by different things because it's not as simple as the last problem. So we're going to multiply the top one by 7 and the second one by 2. So we'll have 28 and we'll be able to cancel it out. So 28x minus 70y equals 28, and then negative 28x, sorry about the x, plus 70y equals negative 56. And now when we solve this, these cancel out, but these also cancel out. So we have 0 equals 0. You may realize that this was the wrong problem from the book because this was supposed to be 8, and therefore we will have 56 here. So that will equal 0.